To understand the various processes involved in measurements, which allow us to map the manifestation of an empirical property onto a set of symbols and thus build a model of the measurement activity, it is necessary, first of all, to grasp the reason why we measure. Measuring is not a self-contained activity, but is a goal-oriented one. We measure because, based on the obtained result, we want to make a decision that will allow us to identify the most appropriate actions to achieve goals set under given conditions. For example, when we drive, we measure the speed at which we are traveling in order to decide whether to speed up or slow down. The goal is to arrive at our destination on time according to the conditions of the traffic, the weather, the speed limits, and so on. All of this can be graphically summarized in this block diagram, which represents the reference model. As you can see, we are still building a bridge between the empirical world, where the object to be measured is found, and the world of symbols, where all the processes take place that, starting from goals and conditions, lead to defining the actions necessary to achieve those objectives. The first element is identification. First and foremost, it is essential to define objectives and conditions. Only after their definition can we identify the measurement, that is, the property best suited to achieving our goals, or rather, the one capable of providing the most meaningful information. Next, it is also necessary to identify the most suitable measurement system, that is, the one which allows us to obtain the best possible information about the measure. However, that's not enough. The environment must also be identified because variations in environmental properties such as temperature, humidity, pressure, and radiation can cause changes in the measurement result. The properties that have a significant effect are called influence quantities and must be kept under control during measurement activities. The passage of time can also influence the measurement result, for example, due to possible drifts in the instruments. Time, unlike influence quantities, cannot be controlled, and therefore, as we'll see later, its effects must be managed with dedicated processes. The second element of our diagram is a modeling block. It concerns the processes that allow the measurement context to be described in mathematical terms. At this stage, a mathematical model of the measurand and the interactions between the measurand, the measurement system, and the environment is identified. The properties are described by variables and the interactions by functions. For example, if one wishes to measure the length of a metal bar, it is known that the length depends on temperature, which therefore represents an influence quantity. The bar can be geometrically described as a parallelepiped, which at temperature T0 has a length L0. If the temperature increases to T1, the length of the bar grows to L1, and this is the linear function that allows one to obtain L1 starting from L0 and the increase in temperature. Therefore, the obtained model allows us to determine the length of the bar at temperature T1, even though it was measured at temperature T0. Once the measurement context has been identified and described, one finally has all the necessary information to carry out the measurement correctly, reaching the experimental processes of the model. These must be considered each time according to the measurand and the measurement system identified. As one can easily imagine, Measuring the length of an electric cable requires tools and operating methods that are very different from those needed to measure the current flowing through it. We have therefore reached the final step of the measurement activity, the decision-making process. Generally, this consists of comparing the measurement result with a predetermined value, for example, a tolerance in an industrial production process or a legal limit. If one considers only the measured value, this operation may seem very simple, since it is a matter of comparing two numerical values. However, we have seen that the measurement result is defined as a set of values, and this makes the comparison much less straightforward. Generally, this set of values is a range of values, and it may indeed happen that the value with which one wishes to compare the measurement result falls within this range. A doubt then arises as to whether the measured value is actually greater or lower than the value with which one wishes to compare it. This doubt is closely linked to the possibility that the decision taken may be incorrect. As we will see, one of the tasks of metrology is precisely to quantify this doubt by expressing it in terms of the probability of making an incorrect decision. However, there is another decision-making path which consists in verifying whether all the goals of the measurement process have been achieved without violating any of the imposed conditions. As we will see later, this step is important for validating the entire measurement process, particularly from the perspective of accrediting the measurement process. To summarize, we have developed a model capable of representing the various steps necessary to carry out a measurement correctly. The question we can now ask ourselves is, how can we use this model? How does it help us to obtain metrologically correct measurement results? We have already seen that a measurement result can only provide an approximation of the true value of the measure, and we can perceive that the causes lie precisely in the various elements of the model we have analyzed. A more in-depth analysis of this model will therefore allow us to identify the origin of such approximations, or to use a term that is correct from a metrological point of view, the different contributions to measurement uncertainty. Understanding their origin is therefore the first step towards their evaluation.